Hello everyone, my name is Erica Faulkner and my partner is Harsha. We will be discussing the spatial and temporal redundant probabilistic inference networks for improving the error rate. Research in the past has usually focused on software implementation of deep belief networks for the conventional von Neumann architectures. Although they are poorly matched due to the processing flow, due to requiring significant execution time and energy caused by the memory processor bandwidth bottleneck, which is intensified due to the large matrix multiplications that are required. To train our software, we pass 60,000 training images that look like the image above into the PinSim network using the labels. To test our images or to test our software, we pass 10,000 test images into the PinSim network. Using MNIST data set, we train and test our network. We then compare the obtained values with actual results to calculate the error. Our software implementation was ran through MATLAB. We found that the error rate is good, but the execution time is large. The motivation for implementing a dedicated hardware is to improve the execution time without compromising the error rate. In future slides, we talk about the current hardware designs with ADC converters and their respective error rates that were calculated by using the SPICE simulation tool. We present a better circuit for improving the error rate compared to commonly used circuits. Consider a 784 by 10 topology. If we wanted to input an image that represents a 4, we would expect the max voltage to represent a 4 if it was ran properly. Therefore, hardware-based RBM design research seeks to surmount certain limitations. One RBM is enough to implement this topology. The total resistors that was used in the crossbar array was 15,680. Now let's consider a larger topology, a 784 by 200 by 10. For this topology, there would be 2 RBMs that are required to implement it, and the input and output classes are defined in the figure below or to the side. The accuracy of this network is much higher compared to that of the previous topology, which was the 784 by 10, but the power consumption is higher due to it being a larger topology. As the number of layers increases, the weights and biases are adjusted more precisely. Total resistors used in the crossbar array is 317,600,000. Let's consider another topology, 704 by 500 by 10. This one also requires 2 RBMs to implement the topology. The input and output classes are shown above or to the side. The accuracy of this network is much higher compared to the previous topologies, but like the previous one, the power consumption is higher due to it being larger. The total resistors used in the crossbar array is 794,000. This is a simple ADC circuit. It is an analog to digital converter that is cascaded to the deep belief network to convert analog input to a digital output. This is a conventional model. It uses more energy and it has less accuracy compared to the ones that we are proposing. We did the hardware implementation through Python and SPICE. This is the table for the PinSim plus ADC. So for the 784 by 10 topology, the error rate was almost 45%. For the 784 by 200 by 10 topology, it was much less. It was only 20%. And for the 784 by 500 by 10 topology, it was 15%. This slide here shows a SCPIR circuit, simple account. This PIR unit is used to interpolate the probabilistic output of the p-bit based output neurons to the digital output. These are the results after the SCPIR. The 784 by 10 topology has an error rate of 41%. The 784 by 200 by 10 topology has an error rate of 19, and the 784 by 500 by 10 has an error rate of 14. This is a SSPIR circuit. It is used to manipulate the probabilistic output of the p-bit based output neurons to digital output. It is more reliable compared with the SCPIR unit. The results after the SSPIR plus Pinson was for the 784 by 10 topology. We can see that it was reduced by about 4% to 38%. For the error rate. For the 784 by 200 by 10, it was reduced to 17, and for the 784 by 500 by 10, it was reduced to about 13% for the error rate.
In this slide, we're going to discuss about the spatial triple modular redundancy, where you can see the figure that a single network is replicated 3 times, and the output is seen at the 3 input majority gate. So we try to give similar input to all the networks present here, and so if a network causes an error, the 3 input majority gate is going to fix the error, and the output is given as shown in the figure over here. So as you can see, the top 2 networks perform well and gives the correct output, whereas the last network shows the wrong output. So when we transmit the outputs to the input of the 3 input majority gate, it does the majority operation and gives the output based on the majority number of inputs over there. So this is the functioning of spatial triple modular redundancy. So in this project, we implemented this network using simulation tool like SPICE. So because we don't have a fabricator hardware to do it, so I'm going to discuss about the Pinson framework, where the simulation, the flow is done. So we input the training images to the MATLAB file. It generates weights and biases, and the Python file is going to be used to integrate a SPICE rbm.sp, and the test inputs and test labels are used to calculate the error and power consumption. So this is the flowchart flow of the Pinson framework. And when we move forward, I just wanted to show you how the output files looks like. So as you can see, the first file generated is going to be analog. So we are trying to test the circuit with 100 test images. So the pbit in.txt is the analog file that is generated for 100 images, but because there is no space, I'm just showing you for 4 images, because the number of classes is equal to 10. The total number of analog values generated for each single images is going to be 10, and these analog values, analog output is going to be transmitted to the PIR circuit. So in this case, we are just looking at the SSPIR circuit. So the image 1 analog values are transmitted to the activation function over here, which is the activation function is a sigmoid activation function, and the output is going to be transmitted to the integrator circuit, and then to the PIR circuit, which converts it to the digital output. So the analog output is going to be converted to digital. One more thing, this analog output is going to be is not going to be at the final layer. It's going to be just before the final layer. So these values are different compared to the final layer analog values. Yeah. So the C portion, the C section represents the digital output. So for digit 0, for digit 1, digit 2, digit 3, until 9 for different images. So for image 1, it is converted to digital, and as you can see, digit 7 goes all once, which means the input image is 7. For image 2, the input image is digit 2. Also, you can see the digit 6 has some kind of value other than all ones. Because digit 2 is the highest, we treat this as the final output instead of digit 6. So that's how the output is evaluated. In case of spatial redundancy, we have 3 different networks. So each network generates three different digital output files, like input 1, input 2, input 3. It generates output 1, output 2, and output 3 for different networks, for the 3 networks. So after generating the 3 digital output files, each image is then transmitted to different 3 input majority gates. So if you consider image 3, image 3 has digit 2 as the final output for the first network. The first network shows that the image 3 is digit 2, and the second network says the image 3 is digit 1, and the third image 3 says uh, the third image says it as digit 2 as the output. So if you take digit 2, if you consider digit 2, we are going to have all the different 3 input majority gates at each and every digit. So for 9 digits, we have three majority gates. So 3 majority gates multiplied by 9, 27 majority gates for each image. We have 27 majority gates. And then these 3 digits are then transmitted to the majority gate over here. So it is going to give the output based on the majority values. So the final output at digit 6, at digit 2 is going to be 111, because instead of 001, which showed in the image 3. So these are the error rates calculated for the spatial redundancy with SSPR circuit. So we implemented this for 784 by 10, 3 different topologies. These are the error rates as you can see. For 784 by 500 by 10 network, the error rate is going to be 0.1. For 784 by 200 by 10, it's going to be 0.14. By 10, it shows 0.305. And these are the power and power consumption for all these different networks. The total power consumption for 784 by 500 by 10 is going to be high. Also, this is the power is going to be in milliwatts over here. And also, there is an alternate model for reducing the power consumption, which is a temporal triple modular redundant network. So this is this temporal triple modular component is going to be implemented at the final layer. So this is the actual figure for temporal triple modular redundant. So we try to input. We try to use a single network instead of 3 networks. We give different images to the network, and the similar images 3 times to the network, and the output is calculated at the end of the majority order. So this is the block diagram for the temporal triple modular redundant. Images transmitted to the belief network, then PIR circuit, then temporal triple modular redundant circuit. So evaluation metrics. the final evaluation metrics metric table is the figure that you are seeing here. So after doing the software implementation, the error rate is 0.04 for 74 by 500 by 10 network. That's for software, and because the software implementation is minimum error rate, but the execution time is very high. We are just comparing the hardware error rates. So the first hardware error rate that we shown here is ADC circuit, the pins with ADC and the pins with SCPIR, SSPIR, and spatial SSPIR and temporal SSPIR. So as we move from left to right, the error rate is going to be reduced because ADC gives the highest error rate, and SCPIR is similar to ADC, but a little bit less compared to ADC. SSPIR does a good job with error rate, but when you come to the spatial redundant SSPIR, the error rate is going to be reduced even more. So, which is a good sign, and the least error rate that we could achieve using spatial SSPIR is 0.1, and it is expected that temporal SSPIR could achieve similar error rates compared to spatial SSPIR, and yeah, it's going to be in between SS and spatial SSPIR. And yeah, this is a graph for different topologies for different hardware circuits. So the first, as you can see, the 784 by 500 by 10 circuit has minimum error rate for all the hardware implementations. Spatial redundant circuit outperforms all the hardware networks. The yellow bar graph represents the spatial redundant SSPIR, and the least error rate that we could achieve is 0.1 for 784 by 10. And yeah, thank you. These are the references that we have used. And